Hi, my name is Catarina and I'm a third-year PhD student at University College London, working with Irania Puris and Jason McEwen on classifying supernova in PLAsTiCC data using snmachine. This work is in preparation for the Rubin Observatory Legacy Survey of Space and Time, or for short, LSST. The observatory is being built in Chile, and it will observe the southern half of the sky every few nights. Its main science goals are taking an inventory of the solar system, mapping the Milky Way, probing dark energy and dark matter, and exploring the transient optical sky, which is the goal I most focus on. LSST is considered wide due to its large sky coverage that can be seen in the image. Deep, because it can reach magnitudes as faint as 25-28. And fast, because it's able to survey the available sky roughly every 3 nights. The survey will last for 10 years, and every night it will get roughly 10 million alerts. However, we are unable to follow up all of them because we don't have enough resources. So we must choose which ones to follow up. However, it's also impossible to visually inspect all of them. So we need an automated pipeline to decide which ones we want to follow up. In preparation for this challenge, the Photometric LSST Astronomical Time Series Classification Challenge, or for short, PLAsTiCC, was launched in 2018. This open data challenge asked the participants to distinguish between different types of transients and variable stars. The data was a simulation from LSST, and it included the parts of periods of time where there were no observations of the events. And this happens due to that source not being visible at the time from LSST's site. This challenge also had the problem of the training set not being representative of the test set. Photometric classifiers are usually trained on a spectroscopically confirmed dataset. The spectroscopy is better to accurately classify an event, but it takes more time, so we are unable to do that for all the events. Additionally, it's easier to spectroscopically observe events that are brighter and nearby. So this dataset has a bias towards that. In order to obtain a good classification, we need the training set to be representative of the test set. So part of our work is to find a way to make the training set more representative. And this will involve some domain knowledge. Overall, the data was successful, with many entries and approaches to this problem. In this project, we focus on a subset, on distinguish between different types of supernova. And we choose to use snmachine. This is a Python package that is flexible and modular, and it's good to classify different types of supernova. It allows us to choose which type of features we want to use and which classifiers. For our supernova problem, we chose this pipeline. First, we input a training set. Then, we make it more representative of the test set by augmenting it. We extract some wavelet features and train a gradient boosting decision tree classifier. And after that, we are ready to train to classify new events. A wavelet feature is a model-independent features, and it allows us to do a wavelet transform, which is a frequency transform. It is similar to a Fourier transform, but instead of being defined only in frequency, a wavelet transform or decomposition is localized both in space and frequency. We also chose one that was approximately invariant under translation and stretch. Wavelet features are general features, and they work for many classes of transients, and also many classes of time series events. But how do we do it? So we start by looking at our data. It is not homogeneous. We don't have observations in all the passbands at all the same time. So we start by interpolating between the observations. We use a Gaussian process fit because it allows us to include the uncertainties on the observations. Then we use the Gaussian process to predict the fluxes in a uniform grid of times. Using that grid, we perform a wavelet decomposition. However, this results in a highly dimensioned feature space, and many of the dimensions do not provide any insights in our problem. Additionally, with such a higher number of features, our classifier is unable to accurately classify and distinguish the different types of supernova. So, we reduce our dimensionality using a principal component analysis, PCA. Of course, we can always go back to the original space and see how much information we lost, how much different the shape of our light curve is from the original fit. But note that on this problem, we are not interested in replicating the original light curve, but only to get shape information that is good enough to distinguish between the different types of supernova. So for our problem, we start by reducing the large light curves into only the transient part, the part that actually allows us to distinguish between the different supernova. In this way, our longest light curve is 254 days. Then, we fit a two-dimensional Gaussian process, which fits them both in time and wavelength. This allows us to get more realistic light curves because it uses information across wavelengths. And you can see in the image that they look more realistic. And they are also able to predict the fluxes in wavelengths where we do not have any information. Finally, we choose to keep only 40 PCA components because that's what perform better for our analysis. Then we need to do the augmentation to make the training set representative of the test set. We start by withdrawing new light curves from the Gaussian process fit to the original data. Since the Gaussian process was fit both in time and wavelengths, we are able to predict its fluxes for wavelengths we did not observe, and hence we are able to change the distance that the event is from us, or the redshift. This allows us to make the training set more representative by putting some events that are farther away from us. This augmentation was based on the avocado approach. In addition to changing the distance, we also degrade the resulting light curves because the light curve quality of the test set is much worse than on the training set with low redshift and bright events. For the classifier, we choose a gradient boosting decision tree. Its predictions is the sum of several decision trees that are iteratively fitted to the residuals. We then optimize its hyperparameters by maximizing the performance of a 5-fold cross-validated grid. However, we must take into attention to avoid data leaks. So, all the augmented events that are generated from the same training data, from the same event, are kept in the same fold during the 5-fold cross-validation. For the optimization, we choose a log loss metric because it's a multi-class metric that incorporates classification posteriors. And it was also the metric that was used for the PLAsTiCC challenge. In the augmentation, we can start by augmenting all the original events the same number of times. However, our training set is also unbalanced, and not all of the supernova classes have the same number of events. Looking at confusion matrices, we see that most of the events are predicted as supernova type 1a, which is the most common class. The confusion matrix on the diagonal tells us how much our classifier is being correctly classifying, and in the off diagonals, it tells us what are the events being misclassified as what. In order to solve this bias, we simply augment the events such that every supernova class has the same number of observations. And now we can see a stronger diagonal, and most of the events are correctly classified. In conclusion, wavelet features are general features that work for many types of transients and time series events. And that to have a good classification, we require a representative and balanced data set. To solve the representative, we explore the training and test set differences and map them. So we can use the map to augment the training set, create an augmented training set that is more representative of the test set, and then classifying it. In many cases, this will require domain knowledge to know what type of transformations we need to do in the original training set. And to balance the training set, we simply need to augment such that the different classes have roughly the same number of events. Thank you.